All right, it's time to start Math 1151. Today we're going to do 4.5 linear approximations, or I think that's what it's called, linear approximations. All right. So here's the idea. I'll give you the general idea, and then we'll work some examples. The general idea is really simple, but it's so simple that you can understand the sort of general idea and then not know how to do the problems because they don't seem to be connected, even though they are. So let's see here. I had a piece of paper someplace. I had an important secret piece of paper. Forget it. Okay. So if we can take the derivative of f of x at x equals a, if we can take the derivative of f, if it's something that we can differentiate, then the linear approximation of f of x at x equals a, and this is what we're talking about. We're talking about the linear approximation is L for line, L of x is equal to f prime of x times a times x minus a plus f of a. You might wonder, why would anybody ever care about such a thing? Here, let's do an example. We're first going to do an example in your head. We can all do this. Somebody tell me, what's the square root of 26? What's the square root of 26? 5 point something. It's 5 point something. That's the idea here. What you did is you took a square root that you know, and then you know this is a little bit bigger. So let's do that example, but with a linear approximation. That's the sort of thing that we do. We want to know, so question. What is and we're pretending that we don't have calculators around. This is the idea, because sometimes you can't do the calculation. I worked on a project for some people with a steel mill, and we wanted to solve a very tough equation. By the way, when we compute the square root of 26, what we're doing is we're solving the equation x squared equals 26. They're the same thing. So in my real life, I had to solve a very bad equation. I couldn't do it by hand. I couldn't even tell somebody how to do it. The best I could do was cook up a computer program that would solve it after like 10 minutes. In real life, it needed to be solved instantly. So what do? Well, instead of solving the real equation, we set up a linear approximation and we solve a fake equation. And it's good enough. So instead of solving the hard equation, you solve an easy equation. Make sense? So I want to know, what is the square root of 26? So here's what we're going to do. First, we turn it into an equation. Now let's see. Is this really what I want to do here? Yeah, this is what I want to do here. And so we want to have x squared equals 26. So x is equal to, so the square root of x is equal to, I'm sorry, I'm being stupid here. Bart, you should just think, yeah, okay. So what I'm going to do is I'm going to approximate f of x is equal to the square root of x. And we're going to do, where's a square root that you know? What's a square root that you know that's near 26? 25. We'll do it at x is equal to 25. Now, can you tell me the derivative of f of x? Can you tell me f prime of x? F prime of x is equal to 1/2 times 1 over the square root of x. Isn't that right? All right. Now we're going to go to our linear approximation. We don't really need to you don't really need to memorize this formula. What formula is this that I'm using here? There's a 2-word answer to this. This is the point-slope formula, right? Oh, good. People are looking confused. That's good, because then I know that I should explain it better. All right, so this is just the point-slope formula. F prime of a, this is the slope of the tangent line. This is a slope, right? And what we're doing is we're finding a line when x equals a. So this is like x naught. Right? And then we have, this is y naught. So this is like x naught, and there's y naught. This is just the point slope formula. All right, so we have this, so I know f prime. F prime of 25, so here a equals 25. You don't need to tell me that, but I'm just telling you this so you can see the parallel with the formula. F prime of 25 is 1 over 2 times 1 over square root of 25, right? Oh, and the square root of 25 is equal to 5. So this is equal to 1 over 10. All right, great. So how does this help us? Well, our linear approximation now, L of x, I say, well, that's 1/10 times x minus 25 plus f of 25. F is square root of x plus 5. I'm going to do some simplification. So this is x over 10 minus 25 over 10 plus 5. 25 over 10, that's 2.5, isn't it? Right? Okay, 2.5. Oh, 5 minus 2.5 is 2.5. Okay, so this is equal to x over 10 plus 2.5. Now, let me just show you what's going on geometrically here. And then we'll get our answer. So if this is x, and here's y, and we're plotting the square root, we should start to know what these functions look like. This is the square root of x. And here I'll put down, this is supposed to be 25 right there. Our linear approximation is going to look like this. It's the tangent line that goes through that point, right? That's exactly what it is. And so now when we want to know what the square root of 26 is, or we want an approximation, what we'll do, 26 here, we'll just evaluate it at that blue line, which should be close to the right answer. That's the idea. So I'll go ahead and finish this off by hand. Somebody should get a calculator out and see how far off we are. So what we should do is we should compute L of 26, right? And that's equal to 26 over 10 plus 2.5. So this is equal to 2.6 plus 2.5. That's equal to 5.1, a little bit over 5, right? And what is the square root of 26? I have no idea. Somebody have a... Oh, she's doing it for us right now. Thank you. 5.09 stuff, right? So this is definitely approximately equal to 5.09 stuff. So that works out really nice, right? This is a linear approximation. So one of the ways, it's kind of a... Now look, I want to point out something. We didn't work very hard to do this. What we did was we picked a number that we already knew the square root of 5 for. And we used that to help us do all the calculations. All right? What questions do you have? This is like one of the prototypical examples. What questions do you have about this? Yeah. You work, he says, just for clarification, you basically work with an a. And this a should be some value that you know how to evaluate your function at already. All right? So if you're doing a cube root, you need to work with a cube, like 27, right? And then you don't plug in the thing you're approximating until the very end. Okay? All right. Let's do another example like this because I remember, I don't know, is this confusing? I remember thinking this was really confusing when I first learned it. You know, how do you use derivatives to compute square roots? I don't know. That was my answer. That was mine. Okay, so let's go ahead and do, oh, this is another great example. Okay, let's do, so I'm going to erase this. Let's compute sine. So I want to know, okay, use a linear approximation of f of x is equal to sine of x at x equals 0 to approximate sine of 0.3. Has anybody ever seen sine approximated with a small number before? Have you guys seen this in your classes? No? How many of you are engineering or physics people? Okay, you'll see this. I mean, this is a standard trick to do. And we're going to explain why it works, basically. So I want to compute a linear approximation to sine of 0.3. And what is a linear approximation? It's just the fancy word for the tangent line at x equals 0. That's all it is. It's just the fancy word for that. Now, you can't dismiss it because then we're going to ask you to compute a cube root or something like this. And you're like, wait, how do I do that? OK, so let's approximate sine of 0.3. This one's almost easier. So if f of x is equal to sine of 0.3, oh, sorry, sine of x, what is f prime? It's equal to cosine. OK, so now I can, oh, and what is f prime of 0 equal to? Cosine of 0 is, oh, it's 1, right? Cosine of 0 is 1. OK, so now our linear approximation, L of x, is going to equal to, so we plug in the slope. And what's the slope? It's 1, right? Well, that's easy. 1 times x minus the place we're approximating around. Oh, that's this point right here, I think, right? X minus 0 plus, and now I plug in, right here, I plug in, this is going to be f of 0. And so sine of 0 is 0. That's right. That's right. Sine of 0 is 0. Oh, and then this is just equal to x, the linear approximation of sine of x at x equals 0 is just x. And let's see a picture of this. All this is saying is that if you plot sine of x, and I plot the line y equals x, that they share a lot of ink when you put them together, right? This is x here. And so what this tells us is that sine of x, sine of 0.3, let's write that down. Sine of 0.3, that's interesting, is approximately 0.3. And if you type this into your calculator, you're going to find out that sine of small angles is basically just that angle, right? This is useful because sine is hard to work with, relatively speaking. But the function x is super easy to work with. By the way, if you want to see another way to see this is true, what's sine in terms of a triangle? How do you explain sine in terms of a triangle? It's opposite over hypotenuse, right? So if I make a long, skinny triangle, look at that right triangle. That's a good one. Okay? Here's a small angle, right? Sine is A over B. You can kind of see that, let's see, what would x be? Maybe that's not so clear. I don't know what I'm talking about. I can't see it right now. I thought that made sense. But anyways, this makes sense. It makes sense to me that maybe I should put it on a unit circle. Oh, that's what I should have done. You put it on a unit circle. Here's a unit circle. Aha! Put it on a unit circle, make a small angle, right? Sine of x is opposite over hypotenuse, right? Well, when this angle's small, this height is almost that arc length. And so that's another reason why sine of x is approximately x. What? I just drew a triangle inside a unit circle. I drew a triangle with hypotenuse 1. Well, whatever. Okay. So, those are linear approximations. Let's do another example of a linear approximation. Let's see. We're going to talk about differentials later. Oh, wow. Okay, let's do this one. Okay, use a linear approximation of f of x equals the fifth root of x at x equals 243. 243. Okay, fifth root of x at 243 to approximate the fifth root of 250. Oh my goodness. 243. What do you think that's the 3? Oh, 3. Good. That's great. So 3 times 3 is 9 times 3. 3 times 3 is 9 times 3 is 27 times 3 is 81. Times 3 is 243. Okay. Well, obviously, 3 to the 5th is equal to 243. OK, so now, what do we have to do? Well, we have to compute our linear approximation. That means computing f prime of x. We're computing the slope of the tangent line of f of x at x equals 243. So f prime of x. That's the cool thing about derivatives. They help us optimize things, and they help us approximate things so we can actually compute stuff. That's really nice, you know. F prime of x is equal to, oh yeah, it's equal to this. Something over 5 times 1/5 minus 1 is 4/5. Is that right? Oh, goodness me. X to the 4/5. Yeah. OK. Geez, how do we do this? Well, now I can compute f prime of 243. That's equal to 1 over 5 times. What is 243 to the 4/5 power? Oh, shoot. Well, 243 to the 1/5 power is the same thing as 243 to the 5th root of 243, right? So this is equal to 5 times 3 to the 4th. And 3 to the 4th is, isn't it 81? Yeah, OK. That's not so bad. So it's 1 over 5 times 81. And if we don't know what 5 times 81 is, no problem. We can go find a 3rd grader someplace, and they will do the calculation for cash. OK? So that's great. So we have 5 times 81. 1 over 5 times 81. That's the slope of our linear approximation. That's right. So L of x is equal to 1 over 5 times 81 times x minus, what's x naught? I'm doing the point slope formula. If you don't know the point slope formula, do yourself a big favor. Memorize it. OK? And then practice it, like during a date or something. Ask, do you know the point slope formula? Well, I do. Bam! OK, so x minus 3 plus, and then, oh, that's 243, isn't it? Yeah, x minus 243 plus 3, right? OK, great. Great, great. Think, Bart. Think. Oh, I can do this. Check this out. So this is going to be x over 5 times 81, whatever that is, minus, now this isn't as bad as it looks, because what's 243 divided by 81? 3. So this is going to be minus 1 over 5 times 3 plus 3. This is equal to x over 5 times 81, 2 minus 1/15. I don't know. Plus 3 minus 1/15. OK, and so now, if we want to, we can plug in 250 here, and we can see how close we are. Does anybody want to do that? You do? Oh. Yeah? Oh! Oh, thank you. Thank you. It's 3/5. Oh, and I can calculate 3/5. I can even do that. 3/5 is 0.6, and plus, so this is equal to, yes, see, this makes things much better. Thank you. 5 times 81 plus 3 minus, plus 2.4. OK, awesome. So now we just have to do 250 divided by 5 times 81, and then add 2.4 to it, and we should get the something really close to the 5th root of 250. Does anybody want to do that for me? No? Yes? I'm cool not knowing. That's my mantra. Don't need to know. That's right. All right, so this is our approximation. So our approximation, our final answer that I'm going to put in this box here is going to be 250 over 5 times 81 plus 2.4. And how do you know if your answer is right at the end of the day? How do you, yeah, you check it, that's right. And how do you check it? What? Oh, graphing it's not going to help. That's a good guess. That's a good guess. How do you check? How would we check to see if this is the right answer? Use a calculator, and then what do you calculate it? You do it. Here, do it for me. Let's see. Well, what do we? It's 250 divided by 5. That's equal to 50 divided by 81. .01. 3.01. Now 3.01 to the 5th power is? So you get your number out, and then you take it back, and you raise it to the 5th power, and you see if you get 250. What do you get when you raise it to the 5th power? I don't know. 250.08. Is that pretty close? Yeah, good, yeah, that's pretty close. So then you say, okay, I'm right. Most of the questions we ask make sense. They really do. Even the word problems hopefully make sense. If you get really crazy answers, you should write, this is a crazy answer, but that seems right, but my math seems right. And that puts all of us at ease, you know. So let's do another one. Here we're going to do everybody's favorite function, log. We can do a linear approximation of log. What's a value that log's easy to evaluate at? Natural log is easy to evaluate at 1. And e. E, right? Right. Or 1 or e. Okay. What's the natural log of 1? 0. You don't need to know much to do this. So we're going to say, let's approximate natural log of x at x equals 1 to estimate natural log of 1.5. Make sense? Now, I don't think this one's going to be as good, because what happens is if your curve, what's natural log look like? It kind of looks like this. It's not very line-like where we need it to be. So we might be a little bit off here, but that's okay. That's the way life goes. All right, so f of x is equal to natural log of x. F prime of x is equal to 1 over x, right? Okay, awesome. So now f prime of 1 is equal to 1. That's not so hard. Here, let's, well, whatever. We'll keep on working. So L of x is equal to, so it's equal to the slope. And the slope here is 1 times x minus the thing we want to estimate, so 1.5, plus f of 1, when f of 1 is 0. Plus 0, that was easy. So L of x is equal to x minus 1.5. It should be 1. Stupid Bart. 1. X minus 1, because you're evaluating. And that's exactly what this guy here said to me earlier. And if I just would have been listening to him and following his instructions, I would have been doing fine. Instead, I'm off in la-la land. OK. Put a parenthesis here. There we go. Oh, so what is L of 1.5 equal to? 0.5. Okay, can somebody compute natural log of, and natural log of 1.5 is equal to, can somebody compute that for me and tell me what we get? 0.405? That's pretty good. That's not bad at all, especially if you consider what natural log looks like. Natural log looks like, draw true, Bart. Looks like this. I didn't label my axes at all. Where is 1? What's natural log of 1 equal to? 0. So here we are. And so when I draw this line, it makes sense that I'm going to be a little higher than the actual answer of my linear approximation, right? I'm trying to, yeah, what's up? He says, well, at what point do you decide that where you're approximating around is bad? Depends on the application, right? If you're playing horseshoes, then you can get pretty far away. But if you're trying to design an engine and you need to have rigorous tolerance, right? Then you have problems. So, next Wednesday, I'll show you how to get as close as you want, okay, without much work. Basically, linear approximations are the first step to something called Newton's method. And Newton's method will solve all nice equations for you if you know how to guess their answer close enough to begin with, which you usually do, because you don't have to be that close. You could even use a linear approximation to do it. Okay. Okay, so now the next topic is a little strange. You guys feel okay with linear approximations? So they're probably going to ask you to use linear approximations to sort of solve some equation or something. You should work some problems here. It's not enough to know that it's just a tangent line. You have to know how to apply it, like we've been. That's the concept. It's not making the tangent line. You guys should already know how to do that. Okay, the next topic is our differentials. Differentials are perhaps a slightly confusing topic. And perhaps of the things that I've taught you so far recently, differentials might be the least important, maybe. Although we're going to try to do some cool things with them. Differentials. All right, here we go. Differentials. So you have f of x hanging around. It's some function that you know. You have f of x, and x is a variable, right? You plug in numbers for x. I'm going to make a new variable. All right? Now, somebody tell me, like, what do you usually name your new variables? H. You could call a new variable h. You could have a new variable y, right? You could have a new variable z, right? You could have, if you wanted to, a new variable called Joe. J-O-E is one variable. You could do that, and then you could have like a function, you know, party of Joe, right? And you could take the derivative, party prime of Joe. That's how good the party's going at different times. For different numbers of Joe, perhaps. Anyways, we're going to make up a new variable, and we're going to give it what you might consider to be a terrible name. All right, here's the new variable, and here's its name. The new variable, make up consider a new variable. This is a variable. A new variable. It's a new variable. dx. Okay? So dx is this thing that we've been writing with our derivative. This is a new variable. This is not the same. This is not really the same thing. When I have like d over dx, I'm putting it in green. This is really kind of like one piece here. It doesn't really separate. And this is a variable. All right? And we're going to make up another variable, dy is equal to f prime of x dx. So that we have the hilarious coincidence that dy divided by dx is equal to f prime of x. Okay? That's sort of the idea here. Two, and another one, and another. Mathematicians don't like this so much, but sometimes people in other fields like this because you can really start to think this gives a way of thinking of d over dx and dy over dx as a fraction. It looks like a fraction. Why don't we treat it like a fraction? I'm going to advise against it, but that's because of my upbringing. Okay? Yeah, differentials are a way of making it work. You're like, I like that phrase, make it work. Well, make it work. Here are differentials, Bart. What are you going to do about it? This is a new variable. Oh, God. Here's another new variable. It's equal to f prime of x times dx. Therefore, by math, dy divided by dx equals f prime of x. You're forced to accept it. And then I go home and cry or something. You know, so, right. So this is what a differential is. What's it mean? Well, there's actually something kind of cool that we can talk about with differentials. So if I have this picture here, if I have my curve here, dx is sort of like a little change in x, sort of. You're changing by dx. And so I'm going to go over here. And then dy is how much your function changes. This is dy, and this is dx. Your function changes by dx. The x changes by dx. Your function changes by dy. There we go. And look, what is the derivative? If I ask you if I see you on the street and I say, hey, what's the derivative? What do you tell me the answer is? Slope of the tangent line, right? It's the slope of the tangent line. You can see look, if we make the tangent line here, this literally is the slope of the tangent line. That's what's going on. Calculus, the same idea over and over and over again, different stuff. So now look, differentials are really the same. Calculus is kind of old, right? It was developed in 1720s or something like this. It was developed in 1720s by Isaac Newton and Leibniz. And Isaac Newton lived in England, and Leibniz lived in Germany, and it was different places, right? And they weren't totally happy with each other. And so one group of people would say, we have calculus. Yeah, well, we have calculus too. And then they'd try to kind of make their calculus different. You know? And this is why we have different notations for calculus. And they've been kind of, that's just why you might say, why do we have so many ways of writing the derivative? Because different people made up different ways and didn't want to accept other people's ideas. That's okay. But this is all we don't actually use Newton's notation anymore very much. Okay, so yeah, that's nice, Bart. All right, so let's do another simple example, and then I'll show you something else. Okay. So here's another. So what was the first example we did before? We did the square root of 6. Is that what we did? Square root of 26. So, okay, so use differentials. to compute one way that you can know you're right without having somebody around is you try to solve a problem many different ways. You solve the problem different ways. If you get the same answer or a similar answer solving it both ways, then you think you're right. So we're going to try to use differentials to compute the square root of 26. All right, so here's the idea. What we'll do is I'm going to draw a picture so we can see what's going on. And I'll use all the same color coding as before. Here's the square root function. There's the square root of x. And now what I do is I put in 25 here. Now what's the change in x as we go from 25 to 26? 1. In some sense, I don't know. In some sense, I kind of feel like differentials are a little bit easier. Once you get used to thinking about this way, you're like, oh, that makes perfect sense. I like it. You know? Maybe we shouldn't be so down on them as mathematicians. Okay, so there's 26, and then we want to know how much the curve went up, right? That makes sense. Oh, and what am I supposed to do to compute? And that's dy. How much the curve went up? That's dy. So that's dy right here. So really, we want to know what dy is. And what's dy? It's f prime of x dx, right? Okay, so let's compute f prime of x dx. Okay, so square root of x. Oh yeah, this 1 over 2 square root of x. All right? So this is f prime times dx, whatever that is. Dx is that variable, right? And how big's dx here? 1. So it's 1 times 1 over 2 times the square root of 25, which is 5. So this is equal to 1/10, right? So dy, oh, that says this is equal to dy. This is equal to dy. And dy is just that other variable, right? That's all it is. I know it has the d in there and the y, but it's really just that other variable. And so what am I supposed to do here? Well, look, if I go over this far 1, I go this far up dy. So what's this point on my curve going to be then? This is here. That's 5, right? So this is about 5.1. And was that about the right answer before? Did that seem easier than the last time? Yeah, I think so. Maybe it is easier, but it's a bit more conceptual, right? It's less like, do this, do this, do this. It's more, what's going on? How do I think about this? This is really, if you think about it, when I asked you at the beginning, I said, what is the square root of 26? And you said, oh, it's a little over 5. This is more how you did it in your head. Because you said, OK, what's a number that's close to 26? I can take the square root of 25. What's the square root of 25? 5. Oh, now I need to go a little higher. The dy is the little amount higher. All right. So I think this next question is my favorite question. I like this one. Oh, I just erased my differential definition. Oh, well, I'll remember. OK, so suppose you're painting a sphere. What a crazy question. You know, who's ever, OK, so wait, if you're making a Christmas ornament, right? You could be painting a sphere then, right? So, OK, suppose you are painting a sphere. Oh, no. OK, good. With a diameter of 40 meters, with a diameter of 40 meters. I don't know what this is. Some reason we're painting a sphere. I hope they're paying us a lot. OK. You want to apply paint so that it's 0.02 centimeters thick. That sounds good. We want to apply paint 0.02 centimeters thick. What's the next question? Finish the question off for me. How much paint do you need? How much paint? Here's what we'll use to help us. We know the formula. The volume of a sphere is equal to 4/3 pi r cubed. This is the volume of the sphere. And so what we're going to do is we're going to, remember we have our sphere here. Its radius is 40 meters. Oh, goodness. And what we're doing is we're going to imagine it. Its diameter is 40 meters. Its radius is, thank you, 20 meters, right? We're going to imagine it changing in radius here. And we'll use differentials to compute the amount of thickness that we get. That's the idea. So how do you compute? We're going to imagine how much thicker will the radius get? 0.02 centimeters, right? The radius is going up by 0.0002 meters, right? So we're applying a dx of 0.0002 meters. Yep. Why don't we want surface area? Let's just finish this one and then we'll talk about it. Okay? We'll be okay. Mostly, I'll get there, okay? So now, we want to know how much the volume's going to change as we increase this a little amount, right? So how do you compute dV? What's the derivative of the volume? With respect to r. It's 4 pi r squared. And do you know the formula for the surface area of the sphere? Oh, no, it's okay. It's okay. No, she's right. She said, this is the formula for the surface area of a sphere, right? And so now, this is equal to 4 pi 20 squared times 0.002. And that's about how much paint you're going to need. Now, somebody asked me, so you guys might have noticed this. And so let me explain something really quick. That's the final answer, by the way. Has anybody noticed that, what's the formula for the area of a circle? Pi r squared. What's the formula for the circumference of a circle? 2 pi r, right? This is area. This is circumference. I take the derivative of this to get this, right? Why does that work? Because it's the idea of differentials. When you change the radius by a little amount, you're adding like another, when I change the radius by a little amount, it's like you're adding another ring around it. And so you're adding, that's the sort of idea here.